Hello everyone, today we are going to talk about the chapter 5, Radiation and Spectra. You can see this is a picture of the sun was taken at several different wavelengths of ultraviolet, which our eyes cannot see. And then the color code, so it reveals activity in our sun's atmosphere that cannot be observed in visible light. This is why it is important to observe the sun and other astronomical objects in wavelengths other than the visible band of the spectrum. And in addition, you may recall that we talked about even the nearest star is about 4 light years away from us. So there's no way we can establish physical connection with any of the stars. All the information we know about the stars, such as the temperature, chemical composition, etc., are all from the light emitted by the star. Therefore, it is very important to actually analyze the light emitted by the star. So in this chapter, we will talk about how we can get all kinds of information or property of the stars by looking at the light emitted by the stars. Let's look at what is actually the light and the behavior of light. Light, or sometimes we call visible light, is a type of electromagnetic radiation. Electromagnetic radiation, it is the wave of energy given off by the motion of a charged particle in atom. You may recall that in atomic structure, all the atoms actually have proton and electron. All the atoms, as long as the temperature is not at 0 Kelvin, and the atom is actually wiggling, and this wiggling actually generates a wave that can transmit over the space. So that is where the radiation actually comes from. And other than the wave property, the light, sometimes we call it has the wave-particle duality. It also behaves as a particle. You can imagine some object give off light is just like a lot of small bullets coming from, and each small particle of light we call it a photon. But first, let's look at the light from a perspective of a wave. Let's look at what is a wave and what is the most important property or features of the wave. If you look at the bottom picture, you can see here the wave is this up and down motion. And you can see for a certain amount of time or length, this motion is like a repeat. And one example of the wave you can imagine is a water wave. Whenever there's something move on the water, it will generate a water wave. If you look at the overall shape of the wave, you can see the very top, the highest point of a wave, we call it crest. And the lowest point of a wave, we call trough. And the distance between adjacent crest, and we call wavelength. And you can see, actually, if you look at the distance between adjacent trough, which is the same as the distance between adjacent crest, so which also represents the wavelength. So wavelength is actually when you see after each wavelength, the wave is just a repeat exactly what happens in previous wavelengths. And in the class, or in most of the time, instead of write wavelengths, we use Greek letter lambda to represent the wavelengths. And a wave is not at rest. If you imagine the water wave, the wave is actually at motion. And there's also a frequency represents how frequent, like in a unit amount of time, in 1 second, how many wave crests actually pass a certain position. And we call it a frequency. And usually we use lowercase f represents frequency.
So now I was set to let the wave travel towards right. I'm going to start the simulation. So you can see now the wave is moving, right? And we can define the velocity or the speed of a wave by tracking a certain wave crest to see how fast it's moved towards a certain direction. So that is the speed or velocity of the wave. And also you can see that the motion of the wave, it just means the movement of the wave pattern. So it does not represent the motion of the physical material. Let me give you an example. You can look at the point P here. Point P is actually, you can imagine that it's a physical point. It's a point on the string that have the wave on it. You can see as the wave travels to the right, point P does not really travel with the wave. Point P just moving up and down and up and down, pretty much at the same horizontal location. So that is actually how a physical point travel on the wave. So you can see I can make the wave travel towards the opposite direction. Point P will not travel together with wave pattern. Another example, it might make more sense to you, is that imagine in a big football stadium. Typically, during the break, the audience will make the wave across the stadium, right? But you can see the wave generated by the audience will actually move across inside entire stadium. However, if you look at the motion of individual audience, you basically, if you are one of them, what you need to do is basically stand up and sit down when the time is right, right? You are not really travel across the stadium. So what your motion, one audience in the stadium, it's just like the point P on the wave. What you do is just stand up and sit down. But what is actually traveling through the space is the wave pattern. Now let's look at another simulation to define more of the property of a wave. So you can see in this case, I have a string, and this is a point P on the string, and lambda here represents the wavelength. So you can see all the wave need something to some oscillation or something to vibrate to create the wave. So in this case, we can let the mechanical arm to basically oscillate up and down to create this wave on the string. So you can see then how often the mechanic arm vibrate, it really depends on the frequency. So you can see here, I can lower the frequency of the vibration of mechanical arm. So you can see in the same amount of time, the mechanical arm just go through fewer oscillation. I can also increase the frequency. You can see with larger frequency, the mechanical arm will go through more number of oscillation. So therefore, basically, the frequency of the wave is determined by the frequency of the object that oscillates to create a wave. Another way you can find the frequency is that you can look at start to time, how many wave crests actually pass through a certain point at a given time.
And you may also heard about the speed of light. And the speed of light is how fast the light can travel. And we talk about also the light years the units is also based on the speed of light. The speed of light, c, we usually use c to represent speed of light. It is a constant. It's 3 times 10 to the 8th meter per second. And what is the relation between wavelength, frequency, and the speed of light? It's actually the speed of light is equal to, or can be calculated as, the product of wavelength and frequency. The speed of light equal to the wavelength times the frequency. You can see here we talked about the speed of light is actually a constant. So therefore you can imagine if you have longer wavelengths, you have to have shorter or lower frequency. So their product is the same. On the other hand, if you have shorter wavelengths, that also means the wave actually have higher frequency. So their product will be the same. So just to give you an example, for example, if wavelength is 10 and the frequency is 1, 10 times 1, you have a constant number is 10. However, if the wavelength become 5, and the frequency will increase. So therefore, just make sure their product is still 10. So you can see later on when we talk about, so for the electromagnetic radiation, if the wave has a longer wavelength, it will corresponding to a short frequency or lower frequency. On the other hand, shorter wavelength means with higher frequency. And when the electromagnetic radiation or light propagates through the space. For example, on the Earth, we're able to receive sunlight. However, because we are not very close to the sun, so therefore we are only able to receive a very small amount of sunlight. The amount of the energy and an object at a certain distance can receive from a star is obey what we call the inverse square law. So that means apparent brightness or the amount of energy is inversely proportional to the square of the distance. You can imagine in the solar system, Venus is actually closer to the sun compared to the Earth. So, and Venus is actually have a similar size of the Earth. You can imagine one facing the sun, the Venus, the same amount of the area on the surface is actually able to receive more energy from the sunlight. That is the reason Venus is hotter than the Earth. However, on the other hand, if you look at some other planet, such as Jupiter or Saturn, they are much further away from the sun compared to the Earth. So if you look at the same amount of the area or unit area, you can see you will actually receive much less solar energy from the sunlight. That is why the further away from the sun of the object in the solar system, the colder the object will be. We talk about the electromagnetic radiation. The most familiar type of electromagnetic radiation is a visible light, and which is we can see. And you may heard about the rainbow have 7 different colors, all the way from red, orange, yellow, green, blue, and violet. The reason why we see the light as their different color is because the different light have different wavelengths or frequency. Let's actually start from a red light. The red light actually is the one that have the longest wavelength, therefore the lowest frequency. And as you go to orange, yellow, green, blue, and violet, you actually go through the direction what we call and have a shorter wavelength and therefore a higher frequency. And usually the higher the frequency, the more energy associated with the light. Other than the visible light, there is also other type of electromagnetic radiations, and that our naked eye cannot see. but they are also very important because the stars, the celestial object, especially stars, radiate all the full spectrum of electromagnetic radiation. Therefore, those radiations also contain a lot of very important information about the celestial object. So let's take a look from the type of electromagnetic radiation which has the longest wavelength, which is a radio wave. And a radio wave is also very common in our everyday life, like, for example, your cell phone signal and so the radio station signal, and are all transmitted in terms of a radio wave. You can see even if you sit inside a classroom, you'll still receive your cell phone signal. That also actually indicates a property of the radio wave. Because of extremely long wavelengths, radio wave can actually go around a lot of obstacles. For example, it can go around the buildings and go around the wall of the classroom. So therefore, even you inside the classroom, you are able to receive radio signal for the cell phone signal. And as well, so the radio wave you can see even during the cloudy day, and even if we have atmosphere of the earth, the radio wave from the celestial object can still receive from the surface of the earth. If we go towards a direction with a shorter wavelength, you will see there's a microwave. Microwave is the same wave we use to heat our food in microwave oven. If we go further to shorter wavelengths and a higher frequency, we will have infrared radiation. And infrared radiation, and sometimes we cannot really see it, but we can feel it. We can feel it as the heat wave. For example, in the winter, you may turn on what we call the infrared heater. So it's actually generate a lot of infrared radiation. So therefore, you can feel the heat coming from the heater. And you can see infrared radiation, if emitted by the stars from space, not all of them can go through the atmosphere and reach on the surface of the Earth, because there's like a water molecule or there are other gas molecule in the atmosphere. They will absorb or block the infrared radiation. Therefore, you can see the infrared radiation were not able to reach, most of them were not able to reach the ground of the Earth. Then we have visible light. And the type of electromagnetic radiation has even shorter wavelengths than the visible light, is ultraviolet. You may also heard about ultraviolet, that is actually why you need to apply sunscreen to protect your skin from. You may heard about if you expose to too much ultraviolet, it will increase the chance for a person to get skin cancer. So you can see as we go to shorter wavelengths, therefore higher frequency, and the energy associated with the radiation is actually become higher. So for the ultraviolet, only for the range of ultraviolet actually closer to the visible light, you can see can reach to the surface of the Earth. If we keep going to even shorter wavelengths and a high frequency, we'll see X-ray, which is pretty powerful. You know that when you go to a doctor's office to get an X-ray image, there always a radiation sign to warn you there's a high amount of radiation, and you probably cannot take a lot of X-ray in a year, because X-ray compared to ultraviolet is even powerful. It can potentially cause damage to the DNA or cell, or cause mutation if you expose to too much of X-ray. And The type of electromagnetic radiation that has the shortest wavelength, therefore highest frequency, and at the same time with which is have the most strength or the most of energy associated with each photon is actually gamma ray. Gamma ray is the most powerful radiation, and usually right after the atomic bomb, there's a emit of a large amount of a gamma ray. Gamma ray is more dangerous than X-ray and therefore can cause the damage on our DNA or the cell like a genetic material easier than X-ray. And one bad news is that the stars like the sun, they not only emit visible light, they emit all type of electromagnetic radiation. Therefore, if we directly exposed to the sunlight without the protection of atmosphere, our body will expose directly to this high energetic radiation. You can see this radiation is very dangerous. But a good news is that we're actually living on the Earth. We don't need to worry about too much about X-ray and gamma ray from space. It's because the atmosphere of the Earth were able to block most of the gamma ray, X-ray, and ultraviolet, which very strong radiation that can cause potential damage to our health. So you may have heard about that. The ozone layer actually plays a very important role to block those high energetic radiation. However, for astronauts who travel into the space, when there is no protection of atmosphere from this high energetic radiation, the astronaut will need to wear the protection wear like spacesuit. Spacesuit, one of the most important role or function of spacesuit is protect the astronaut from the strong radiation from the space. You can see that for the entire spectrum of electromagnetic radiation, the Earth's atmosphere we call only opens two windows, and one is radio window. That means the radio wave can go through the clouds, the atmosphere without any difficult. So therefore, it can reach the surface of the Earth. Another window we call is optical window. That means the visible light can go through all the way to the starlight and reach the surface of the Earth. As we also mentioned previously, the speed of light is a constant. Here, remember, the speed of light is not just the speed of visible light. It is actually the speed of all electromagnetic radiation travel in vacuum. So therefore, you can imagine the one with the longest wavelength, which is radio wave, therefore have a lowest frequency, and the one with the shortest wavelength, which is a gamma ray, have actually the highest frequency. Now let's take a look at why the stars able to emit a lot of light. Where this light come from? And so the light the star emits we call is thermal radiation. That is radiation, and the emission depends only on the temperature. So that also means the hotter the star, they basically make it emit a lot of light. And I hope you still remember the state of matter simulation I showed you at the beginning of the semester. As long as there is some temperature, or the higher the temperature, the molecule inside the star actually able to move much faster. So therefore, or you can imagine they're wiggling with high frequency. So therefore, they can actually emit the light with higher frequency. Since we talk about the thermal radiation is depending only on temperature, let's go ahead and introduce a new temperature scale, which we call is a Kelvin temperature scale. So you can see one, we look at the temperature of a star, like the surface temperature. We always use Kelvin, and for example, it's 5,500 K. We always use Kelvin, and which is not as similar as the temperature we use in our everyday life, such as Celsius or the Fahrenheit. The differences between the Kelvin temperature scale and other temperature is that the lowest possible temperature in Kelvin scale is a 0, and the 0 Kelvin represents all thermal motion is actually stopped. That not means the motion of the object, but it actually means the wiggling, the motion of the molecule microscopically inside the object. So therefore, you can imagine there's no negative Kelvin temperature.
To actually explain what it's 0 Kelvin, the absolute zero means, let's just go ahead to use one of the liquid that we are more familiar with, water molecule. You can see, I'm going to cool the container. Let's start with the solid. It's already in an ice state, right? But if you look at each molecule, they are not 100% at rest. Almost all of them are still kind of wiggling around, right? Although they won't travel to any place, but they still wiggling around. So now let's go ahead to cool down the water molecule in ice. So you can see with decrease of temperature, the molecule it just vibrate less and less and less, right? As we approaching 0 Kelvin. It's not easy, even in the simulation, to actually reach 0 Kelvin. So it will take some time, and we are going to get there. You can see now the thermometer showing you it's already in 0 Kelvin, right? What happened to the water molecule inside ice? You can see it looks like Z all freezed, right? None of them move at all, right? So no translational motion, no wiggling, no vibration. So at 0 Kelvin, all the molecule actually lose all this kinetic energy, or we can see lose all the kind of motion. So therefore, the reason why is absolutely zero, because all the molecule they are already stopped. There's no way you can ask the molecule to even lower its speed or even move less, because now they already stopped.
Sometimes we call 0 Kelvin absolute zero because there's no way you can go even lower temperature than 0 Kelvin. All the molecules motion already stopped at 0 Kelvin. There is no way they can slow down even further. Now let's go ahead and look at the detail how the radiation actually depends on the temperature. And we will first look at an example in our everyday life. You may see this kind of radiation cooktop, and you can see before you turn on the switch, one, the coil is cold. You can see it does not glow at all. However, after you turn on the switch, the coil is become hotter and hotter. And when you see the coil, it's kind of emits the red light, it indicates it's very hot. So that also means at this moment, you better not touch the coil. You can see from cold to hot, the object actually radiates differently. And let's go ahead and look at why. When the color gets hotter, it's actually glowing in red. So now let's go ahead and look at what we call this radiation curve, the thermal radiation curve, which is a radiation depends on the temperature. When the temperature is low, and for example, as a room temperature, we typically have like only 300 Kelvin. You can imagine all the electrons or charged particles inside the object at a room temperature actually just wiggling with lower frequency. So therefore, the majority of the radiation they radiate is actually at the lower frequency. Therefore, the longer wavelength range mostly are just a radio wave. So even if the table that is at a room temperature in the classroom, they still radiate, but they only radiate at the radio wave, the range, which our naked eye cannot see. But when we increase the temperature, you can imagine the higher the temperature, the faster or higher frequency the charged molecule or charged particle like electron wiggling inside the object. You can see it start to emit and there are higher frequency light. Just like you turn on the switch of the cooktop, as it increase the temperature, you actually start to emit the light with higher and higher frequency. You can see if you go all the way from a radio wave all the way to the what we call the visible spectrum, the lowest frequency in the visible light is red. So therefore, that is why when the object becomes hotter, it first actually start to emit the red light. If you look at this graph, if we keep increasing the temperature to even higher temperature, you can see the radiation curve actually start to emit an even higher frequency light, like green, blue, and violet light. And however, if you look at the 13400 Kelvin, the red light is actually emitted is still more than the high frequency blue and violet light. Therefore, if you look at the overall color, for example, if it's a star, the overall color of the star is actually still reddish because it's emit more red and orangish light than blue and violet light. With even higher increase of the temperature, you can see the curve, the radiation curve, start to get, there's two effects. You can see the peak actually start to shift from higher frequency. At the same time, it's actually become even higher. And you can see it start to emit more different colored light if we only look at the visible light. For example, at temperature about 5,500 Kelvin, you can see the peak is kind of in a yellowish color. So it's actually only emit a little bit more yellowish than the green, blue, and violetish. So therefore, about this temperature, the overall color is what we call the yellowish white. And you can see that there is two different equation or laws to represent these two effects. When you increase the temperature, the peak of we call it the peak emission wavelength actually shift to a higher frequency, which can be described by the Wien's law. So that is the highest frequency here. You can see the corresponding to the wavelength is they call is inversely proportional to the temperature. So you can see the higher the temperature, the shorter the peak emission wavelength. So that is a wavelength the object emits most of its light at. And the second, we call Stephen Boltzmann's law, is actually describe the height of the curve, the radiation curve. So F just means the total energy emitted by the radiation is proportional to the force power of the temperature. So you can imagine the amount of energy radiated by the object increase much faster with the increase of the temperature. If the temperature is increased by twice, right? And the force power of 2 is 2 times 2 times 2 times 2 is actually 16. You can imagine when the temperature only increased by 2 times, the energy radiated actually increased by 16 times. So that is actually a much larger increase of the energy radiated by the object. And if we look at the Wind's law, so the increase of temperature means the decrease of wavelength, which means it's actually goes through the higher frequency range. On the otherwise, if the temperature is smaller, you can see here, when the temperature is actually lower, the peak emission wavelength is actually longer, which means lower frequency and longer wavelengths. Now let's go ahead to look at the simulation to see what color of the star should looks like at different temperature. So let's first start with the sun. You can see the surface of the temperature of the sun is about 6,000 Kelvin. So if look at the sunlight, it's mostly white, right? So it's more like yellowish white. But if you look at directly, it's mostly white. The reason why the sunlight is bright is when you look at the thermal radiation curve. The top, the peak is pretty much at the center of a visible spectrum. So therefore, the sun pretty much emit the similar amount of like yellow, red light and compared to the blue and the violet light. A little bit more of a yellow and a reddish. So therefore, the sun's color is mostly white, but it's actually a little bit of yellowish. Now, let's go ahead to increase the temperature. Let's go all the way to a very hot star, Sirius A. Now you can see the peak is already go all the way. Let's scale down a little bit. You can see here in Sirius A, which is a very hot star, the surface temperature is over 10,000 Kelvin, and it's actually, if you look at the color of the star, it's a very blue. Let's look at this thermal radiation curve. Remember, we already scaled down the scale. Remember, when this is the temperature of the sun, so this is all already very hot. We scale down a little bit. If you look at the thermal radiation curve, the peak of the radiation is already moved all the way into the ultraviolet range. So therefore, if you look at the amount of visible light it's actually emit more violet and blue light than the red and orange or the yellow light. So therefore, the overall color you see, you look at the Sirius A, is a blue color because, of course, if it emits more blue color than red, the overall color will be blue. Now let's look at maybe a colder star. Okay, so we need to zoom, like make it larger for us to see. If we look at a colder star, for example, if the star's surface temperature is about like 3,000 Kelvin, something about a little bit over 3,000 Kelvin. If you look at the thermal radiation curve, the peak is basically in the infrared range. If you look at how much light it emits, it's actually emit much more red and orange light than blue and violet. So its overall color is red. And if we increase the temperature, you can see as we increase the temperature, it starts to emit more, like in orange and yellow parts, but still much less blue and violet. You can see the color yellowish. And if we increase temperature further, you will basically get like a pure white star. And as we go even higher, as we see the series A, the very hot star, you actually get blue star. So if you remember, we go all the way from red and orangish star to yellow and to white and to the blue star. So you can, from this simulation, you know that blue star is actually hotter, and a reddish star is actually have lowest surface temperature. On the other hand, if you look at the object very cold, for example, the object on the Earth, like the Earth, the room temperature is actually about 300 Kelvin. There are also a lot of objects in the space that is pretty cold, which is even cold than 300 Kelvin. We'll look at how its emission spectrum looks like. You can see the 300 Kelvin is actually, it does not emit any visible light. You can see, you cannot really see it. But the majority of them actually emit are the wavelengths, which is actually at a very long wavelengths, which corresponding to infrared or the radio radiation. Now you can see actually by looking at the star's color or measure what we call the peak emission wavelengths, we're able to calculate and determine how hot the star is. And next, let's look at how we can know what the star is made from, how we know the chemical composition of the star. It's basically look at the spectrum of the star. And so what we're going to talk about was spectroscopy in astronomy. A spectrometer is a device that actually helps us split light into its component color to form a spectrum. So just like here is a prism, or like the rainbow. The rainbow is also the water drop, the raindrop or the water drop in the atmosphere is acting as the spectrometer to split the sunlight into its component color. The different elements actually radiate differently. And there is a three type of spectrum I will need to talk about first. First type of spectrum is what we call the continuous spectrum. It's just like a rainbow color. So you can see if you split the sunlight, it looks like, overall speaking, it's like a rainbow color. It's a continuous spectrum. It's because where does the continuous spectrum come from? It's because we know the inside of the sun is a very hot gas. So therefore, hot solid, liquid, or dense gas is actually produce the continuous spectrum. However, if we take a close look at the sun's spectrum, probably not really able to use naked eye, but we need to use a very sophisticated spectrometer. We're able to see that the spectrum of the sunlight is actually, the background is continuous spectrum, but on top of it is a lot of dark lines. We'll talk about what is the dark lines represents in a moment. And another type of spectrum, they only exhibit a discrete lines at different color. And this type of a spectrum, this bright light spectrum, we actually call emission spectrum. They only have bright lines. And what kind of situation produce emission spectrum? One, the gas is hot, but it's a low density. It's actually produce emission spectrum. It's like a neon light. We feel the neon light, the glass tube, with very low density gas molecule, it can produce the emission spectrum. So here you can see this is an emission spectrum of a different element. For example, if the neon light, if the light filled with sodium, you can see it's actually emit different lines at different color, or sometimes we call at a different wavelengths compared to other element. If it's with hydrogen, you can see mostly they only have like the red light and no yellow line, right? And the calcium and the mercury also emit what we call the emission spectrum differently. So therefore, if we're able to see the emission spectrum, use spectrometer to split light so we can see individual lines. It's just like you scan a barcode of our item in the supermarket. You will, by looking at the pattern of the spectrum lines, will know what kind of element actually inside the material. So this is what we call the emission spectrum. And for the real spectrum of stars, not only the sun, but most of stars, almost all the stars, the spectrum is actually we call it is absorption spectrum. Absorption spectrum is a spectrum with a background is continuous spectrum, but on top of it is a lot of dark lines. And the location of the dark lines also depends on the molecule. For example, just take an example. This is a hydrogen emission spectrum. So you can see the bright lines of red, like blue-green, and violet, two violet lines. If you look at the absorption spectrum of a hydrogen, you will see the background is continuous spectrum, and you will see the dark lines will exactly appear as the location of the emission lines. So that only means this color is actually missing. So therefore, the same as emission spectrum. And the absorption spectrum also give us this series of dark lines, which also can act as a barcode, which basically is a signature of a different element. For example, if we found the dark lines exactly at the location of this location, and we know that the gas must contain hydrogen. And how the absorption spectrum is produced is first you're going to have a continuous spectrum. And when a continuous spectrum goes through cool, thin gas, it's actually produce absorption spectrum. This cool and thin gas molecule are actually able to absorb a certain wavelength to make this absorption spectrum. The reason that the most stars actually have absorption spectrum is because the core of the star is actually a hot, dense gas, which produce continuous spectrum. But sometimes the surface of star actually have cool and thin gas. So therefore, when the continuous spectrum goes through the surface, it's actually produce the absorption spectrum. And we talk about based on the location of either dark lines or black lines, which we can compare to this kind of signature emission or absorption lines location of a different element. Therefore, the spectrum analysis can reveal the composition of the star, what kind of material the stars are made from. Other than the temperature and the chemical composition of the star, we can determine from the light emitted by the star. We can also determine the speed of the star, like how fast it's moving towards us or how fast it's moving away from us. So let's look at the Doppler effects, which actually enable us to tell the speed of the star. Let's first look at a few clips from the Big Bang Theory to look at how Sheldon actually explained what is Doppler effect.
So what time does the costume parade start?
The parade?
Yeah, so the judges can give out the prizes for best costume. Most frightening, most authentic, most accurate visualization of a scientific principle.
Oh, Sheldon, I'm sorry, but there aren't going to be any parades or judges or prizes.
This party is just going to suck.
Oh, come on, it's going to be fun, and you all look great. I mean, look at you, Thor, and oh, Peter Pan, that's so cute.
Actually, Penny, he's wrong.
Not Peter Pan!
I got a handful of pixie dust with your name on it.
No, you don't. Hey, what's Sheldon supposed to be?
Oh, he's the Doppler effect.
Yes. It's the apparent change in the frequency of a wave caused by relative motion between the source of the wave and the observer.
Oh, sure, I see it now, the Doppler effect. All right, I got a shower. You guys, make yourselves comfortable.
Okay.
See? People get it.
Hey, Sheldon, there's something I want to talk to you about before we go to the party.
I don't care if anybody gets it. I'm going as the Doppler effect.
No, it's not.
If I have to, I can demonstrate. Meow.
Terrific.
Nice.
Hello.
So what are you supposed to be?
Me? I'll give you a hint. Meow.
Choo-choo train?
Close. Meow.
A brain damaged choo-choo train?
Meow.
I still don't get it.
I'm the Doppler effect.
Okay, if that is some sort of learning disability, I think it's very insensitive.
Why don't you just tell people you're a zebra?
Why don't you just tell people you're one of the 7 dwarves?
Because I'm Frodo.
Yes, well, I'm the Doppler effect.
Did you already understand what is Doppler effects from Sheldon's explanation? And Doppler effects is actually very easy to observe in our everyday life. And Doppler effects not only apply to the light, but it's also applied to other type of wave, such as a sound wave. One of the most obvious example demonstrates the Doppler effects is from fire engine siren. So we'll start from the moment when the fire engine siren is approaching us, and you will hear the sound. As soon as you can see the fire engine siren pass from us, you will hear the change of a sound. The change of sound is actually change of frequency of the sound. The sound actually become a lower pitch, which represents the lower frequency of a sound. Let's go ahead to hear. You can see, you hear it when the fire engine siren is approaching us. The frequency of a sound is actually higher. When it's just past us, it's actually the pitch of sound or the frequency of sound is actually lower. As Doppler effects, if we apply it to the light, the same as fire engine siren you just heard. One, the light source or atom is actually moving towards us. The light or spectrum lines is actually shift towards the higher frequency, the shorter wavelengths, which shift the color of blue. On the other hand, is objects, or you can see the atom inside the object is moving away from us. We actually see the spectrum line shift towards the red. Red means longer wavelengths and lower frequency. So let's give you an example by looking at the graph. You can see here if the star is actually emit the yellowish light. When the star is at rest, it doesn't matter where is the observer, then all the observer were able to observe the yellowish colored light. However, when the star start to moving, remember when star is moving, the atom, the molecule that inside emit thermal radiation, they actually all moving together with the star. You can see these rings, the series of rings represents the crest of wave the star emits. You can imagine that is a light wave. When the star is moving towards a certain direction at the same time emits a light wave, you can see all the light wave from the front is being compressed. Remember, the distance between those rings represents the wavelength of the light. So therefore, all this, the wave in front are actually have a shorter wavelength, therefore higher frequency. So therefore, the observer actually in front, when the star is moving towards, will observe actually bluer color. So therefore, we call it blue shift. Observe a shorter wavelength and a higher frequency. It's the same idea when you are observer that the fire engine siren is approaching you. However, on the other hand, if you are the observer, that behind that the star is moving away from you, what you see that the wavelengths that emitted is actually get stretched, right? So that wavelength is actually longer wavelengths. As it's longer, we call it red shift, because longer wavelengths and lower frequency, the red color, it just means the longer wavelengths in the visible spectrum. So therefore, the observer will observe lower frequency or longer wavelengths. If it's the yellow color, then it may observe orangish or reddish color, which is also a similar idea when the fire engine siren is moving away from an observer, you will hear a sound with lower frequency. And how much shift to lower frequency or higher frequency? And when the observe, the objects, it actually depends on how fast is the objects moving. For example, the faster the object is moving towards the observer, the more bluer, or even to a violet, you can observe from the light. So therefore, the Doppler effects can be used to measure the velocities of the distant objects. For example, from the Earth, if we try to observe how fast a galaxy is moving away or towards us. And we know that the galaxy also made from primarily hydrogen and helium, which is the most abundant element in the universe. And we know if it is at rest, the absorption spectrum lines of hydrogen, for example, or helium is right at the middle. This is just to give you example, not necessarily exactly the location of hydrogen absorption spectrum lines. And if we know that the spectrum lines is actually have a longer wavelength, which means shift to the right, to the red, and compared to the ones we know what its location it should be at, we know that the galaxy is actually moving away from us, right? Moving away is a red shift. And how fast the galaxy is moving away from it is determining how red the lines actually shift towards the red region. On the other hand, if you observe a spectrum line that is higher frequency, then it should be. We know that galaxy is actually moving towards us. And if the and how fast the spectrum line actually shift from the middle is actually telling us how fast the galaxy is actually moving towards us. So this way we can get what we call the radial velocity. Radial velocity just means it's either moving away or moving from us or moving towards us. If it's just moving kind of across in front of us, That is something the Doppler effects cannot tell. That is all about Chapter 5. In Chapter 5, we talk about electromagnetic radiation, the wave property of electromagnetic radiation, and we also talk about the different types of electromagnetic radiation, depends on its wavelength and frequency. And we also talk about the thermal radiation and why the object with different temperature will basically radiate different color. And we talk about also how we look at the spectrum lines emitted by different elements. We can tell the chemical composition of the star. And finally, we mention the Doppler effects, which can enable us to measure the radial velocity of distant objects.